Welcome to the next session. We were discussing about the concept of tri-state buffer and how it makes the things to work, which is quite suitable for digital circuits to handle multiple pins without increasing the size. Just like a piece of paper, instead of putting it on table, we put in the form of a notebook. So what can we do? The theme is that with the introduction of tri-state buffer, the biggest advantage is we are able to access multiple things through a small access window. So this is something on which we can combine multiple output lines. We extend the concept further instead of single output lines. Now what I would like to have is, we have discussed about a single byte memory cell. We have discussed about a single byte memory cell. That time when we discussed about a single byte memory cell, how it was told to you? The single byte memory cell was introduced to you. I hope that you still recollect it. This in single byte memory cell, we had one basic concept of single bit memory cell. It is having an input pin D and output pin Q, and such 8 are taken together, and we can, when such 8 are taken together, it becomes a cell like this. These are its input lines, these are its output lines, and these are input lines, we call them D7 to D0, output lines Q7 to Q0, and we have put one more pin called as latching pin, that is latch enable pin. That is latch enable pin. So you can put the data on input pins. When you write it, that data remains always available on the output pins. So this is a single byte data cell, single byte memory cell. If you want multiple byte memory cells, you have to go on adding together further. So those many lines would be there. Now we cannot afford to have multiple lines. Just like some I repeat, some standard, whether A4 is a universal standard, it may or may not be, but it is a substantially accepted standard. So A4 is a standard. The notebook size should be of A4. There are legal size notebooks, for the small notebooks, half notebooks, A3 size notebooks, but A4 is a standard. Like that, 1 byte data cell is a standard. So what we do is that any memory block should not have multiple 1000 data lines, only 8 data lines. And also here, since I introduced the concept of memory cell to you in before last few lectures, that time the concept of buffer was not introduced, so the memory cell was having separate input lines and separate output lines. Now we also want to get rid of that. So now what we want, listen very carefully, a single byte memory cell which I intend to be like this. That this is old. So this is the original cell. Obviously, remember that power supply and ground lines are presumed. Power supply and ground lines are presumed. We don't show them separately. So these are 8 input lines, or I will name, just I change the name because D's I am going for data I7 to I0, and output as Q7 to Q0, and the next line called as, we can say, write line like that, latch enable line. So these are 8 lines of the available memory cell. But now what I don't want 16 lines to come out of this cell. Are you getting me? One byte memory cell is having 16 lines, 8 input, 8 output, and this latch enable is separate. So I don't want this bulky arrangement to come out. I don't want this bulky arrangement to be there outside. Whatever should be there should be inside. Whatever should be there, just like what you can say is that when you give some external view to someone, say at your home, you provide a compact arrangement. All bulkier things you put inside. So only one line should come out. So I7 and Q7 should be combined. Is it allowed? There is a problem because it is an output line and it is an input line. So somebody else is putting something here, and if this Q also puts, then there will be short circuit. Therefore, this can't be combined. This can be combined if and only if the outputs Q are coming from a tri-state buffer. There should be a buffer everywhere, so that you take care. When you want, that time only this will put data, else it will be tri-static. So we put this buffer, and this buffer is having one enable line, and then you can combine this line, and that will come as D7, and similar thing will go, just I am showing it like this, and this will be D0. So now listen very carefully. These are very small things, but these are very fundamental. As I said that you are in the first year, the technology is so much advanced, but that doesn't mean that what we can say, you can start with that advanced technology, right? So these few things are very essential for you. Now what will happen? Number one is this is now called as a bi-directional pin. Means if this enable is made one, so this is one enable of the buffer, this is latch enable. If this enable is made one, then only Q will come out on D7. If this enable is made 0, then this pin would be hanging just disconnected. So when I say this buffer, this is D7, and this enable is for all the buffers. This all buffers will be having, I hope it is presumed that the enable pin of these all are tri-state buffers. This enable pin this is input A for individual buffer, input A, output Y, and this is EN. So if this EN is 1, then only A will be transferred to Y. If this EN is 0, then this would be hanging. So just like, and with nothing. So neither high nor low. So this will not put anything here. Then what you can make, through the same line is connected as input. So if listen very carefully, being the initial part I am very slow. From the same lines I can get the things stored inside the memory cell on this by activating this enable, and if I don't activate this enable, then whatever is stored inside the memory chip will not come out, but the pin on which it was coming out, the same pin is used to store what I want. So D7 to D0 are 8 data lines. If I want to write something, then I will give input, means I will connect this data line to 0 or 1. This data line to 0 or 1, I will connect that. But before this is a single byte. Now what I say, this is a single byte read-write memory cell. This is a single byte read-write memory cell, and these are bidirectional lines. Means data lines of this single byte memory cell are to be used for both purposes. For writing something inside and for reading what is already stored. While writing something inside, I should ensure that since I am making that line 1 or 0 externally, the cell itself, the chip itself should not make it 1 or 0, means it should float, it should make the output tri-state. So that time I should ensure that this En is 0. Somehow I will explain all the detailed logic. This En is 0. With this En 0, what I am doing? I am putting data here, and when I put data here, that time I will make this LE1. So En0 LE1, and then I make LE0. So when LE is made from 1 to 0, whatever was put earlier is stored inside. Inside means it is stored here. It doesn't appear here. And when I want it to come, it comes. What I do, when I want this entire to come out, that time this enable should be made 1. So when this is made 1, whatever is stored here is available here. When this is made 1, whatever is put here is written here. So I can use this and this appropriately. There is one again convention. Instead of logic, just a convention. Why means, say, there is no reason why one should have left lane for going, means there is a road and you go from the left side. In US it is from the right side. So there is no universal convention as such, but in digital thing it is assumed that in many things, active low, in many things there is a logic called as active low logic. Means something which is to be enabled is to be enabled, and for that it is called as enable bar. For that it is called as enable bar. Enable bar. Then, so what we do now, this is the single byte memory cell, we enhance it further. Now for this single byte memory cell, we add 3 pins. Now listen very carefully. I give you a diagram. A single byte memory cell is having this as 8 data lines, B7 to B0, like this, and there are 3 lines on a chip select bar, read bar and write bar. So these are the names given, and the logic is active low. Now chip select bar. If this chip select bar is 0, then this buffer, if this chip select bar is 0, then neither reading nor writing happens. If this chip select bar is 0, then neither reading nor writing happens. Now listen very carefully. I will explain you a simple logic. CS bar, read bar, write bar. These 3 are the inputs, and this LE and EN are the outputs. So a small digital circuit you can easily construct with the following logic. If this CS bar is 1, irrespective of these lines. If this CS bar is 1, then irrespective of these lines, this LE and EN both are 0. Means when chip select bar is 1, this buffer, that is which outputs the stored contents on data lines, is disabled. This latch enable, which stores the things put here inside the latch, is also disabled. CS bar 1, read bar and write bar are ignored, both outputs are 0. Now when chip select bar indicates it is active low. Means when chip select bar is 0, then it is said that the chip is selected, and when chip select bar is 1, chip is not selected. As it is not selected, neither operation takes place. Now when chip select bar is 0, read bar is 0, write bar is 1. When chip select bar is 0, read bar is 0, write bar is 1. That time this latch enable is 0 and enable is 1. So you can have a simple combinational logic that you see. This is some simple combinational logic you can make using, means LE is the output, which is combination of CS bar, read bar, write bar. EN is the output, which is again combination of CS bar, read bar and write bar. For this combination, this intended operation should take place. So when read bar is 0, that time this enable bar becomes 1, indicating that whatever is stored here appears here. When this CS bar is 0, just I should have told you another operation first. Just I seek a pardon. CS bar 0, read bar 1, write bar 1. CS bar 0, read bar 1, write bar 1. So say, I hope that in last year you might have been asked by your parents to study something now. So if study is to be done, then if you are ready to study, then either JE or CET, maybe. And if you are not ready, then the question doesn't arise. So if you come on study table, if you don't come on study table, then there is no question. So whether JEE or CET has no meaning if you are not on study table. If you are not on study table, whether JEE or CET has no meaning. Now you are on study table, but say that no JEE, no CET. So means chip is selected, read bar, that is read bar is 1. That is, chip is selected not for reading. Write bar is 1. Chip is selected not for writing. So neither writing nor reading. Now 0, 0, 1, 0. Chip is selected for reading. Reading means whatever is told here should come out. So this must be 1. Now here chip is selected for writing. Chip is for writing means what should happen? Whatever is put here, should be, transferred. So this latch enable should become 1. So chip is selected for writing, latch should become 1. Now chip is selected for reading and writing both. It should be avoided. Avoided means that the user should not use the chip for reading and writing. Because if he is putting something here and say that I am writing and also making reading 1, read bar at 0, then there may be a short circuit. So it should be avoided, but you should not rely on, remember that what is said to be a perfect design. An average design, what happens is that it gives the caution. Average designers give the caution, and depending upon the caution, if the user avoids that warning, then there may be a disaster. But a perfect designer does not depend on the user. If user is doing something which is unintended, he automatically takes care, and if both are active, in that case, the designer himself may decide to give preference to either or reject both. Many options are there. So for this, the designer should give either of this. It should have either of this, this or this. So if reading is, if it is preferred, but at the same time is writing, so that since writing it is expected that he is intending something, so it is better that this enable should be made 0 and this can be made 1, or that is immaterial. So what should happen is that the two things outputting something at a same time should be avoided. So this is called as this is single byte read write cell. Single byte read write memory cell, which is having 8 data lines, 1 select line, chip select bar, 1 read line, 1 write line, and obviously plus 5 volts and ground. 2 supply lines. 1 read bar, 1 write bar, 1 chip select bar, 1 VCC, 1 ground, and 8 data lines. This is single byte memory cell. Now we move next. maybe that you have heard of somewhere, maybe those who are 12th vocational or may have some extra reading, that address line, but address line is not appearing here. Address line is not appearing here. It is why, I will explain. Say what is a, suppose if there is a class in which only one student is there, will there be a concept of roll number? Will there be a concept of roll number? It will not be, because the purpose of roll number is to select one amongst many. The purpose of roll number is to select one amongst many, and unless many are there, the question of roll number does not arise. So for a single byte memory cell, there is no question of address lines. Now I give you a task using 4 single byte memory cells construct what? One 4 byte memory cell. Then you will ask, what is rocket science here? Construct one 4 byte memory cell. Just have 4, have 1, have 2, have 3, have 4. So there will be 4 memory cells, 32 data lines, supply will make common, read bar will make common, write bar will make common, and 4 chip select lines. It's not so simple. We don't want 32 data lines. 4 byte memory cell, and the main thing is that data lines must be 8. Means even though it is 4 byte, data lines must be 8. Means what should happen now? Listen very carefully. I will draw a big diagram. This is very fundamental and you must understand it. So those who want to think on their own, what should they do? They should put a pause and try to solve this on their own. Those who want to, have you got the problem? We conclude this part here and meet for the next part immediately after in the next session. Those who want to solve on their own should come with solving and watch next video. Those who could not do can watch it as it is. So the question is using 4 single byte memory cells. So each single byte memory cell is having, now power supply lines we don't take into discussion at all, these are presumed. So each single byte memory cell is having 8 data lines, 1 CS bar, 1 read bar, 1 write bar. This is into 4. And this one 4 byte memory cell must have 8 data lines. Again 1 CS bar line only, 1 read bar line only, 1 write bar line only, and few more lines. I give a hint, 2 address lines. So those who want to design should continue on their own and then watch the next part. Others can watch the next part immediately if they are unable to solve it. Thank you. We stop.